Okay, vertical circle, prove the relationship 1 over root 5, which is the speed at the top divided by the speed at the bottom. 1 over root 5 is, I like this one because I'd never really seen anything that had root 5 in it. But obviously the speed at the top is going to be less than the speed at the bottom, so we're going to expect that to be a proportion. And 1 over about 2.5. So let's have a look at that. Now, this is for when you have the minimum speed to get round. So minimum speed to get round. So this doesn't apply when you're going faster than that. And that minimum speed, as you all should know, is equal to the square root of Rg. If you can't quite remember how you got that, remember what you did. It's just when the centripetal acceleration, half, or v squared over r, centripetal force is supplied by mg. So we just solve that and we get v equals square root of rg. So that's when this little guy here is at the top and the weight force is supplying the centripetal force. So how do we prove though that that speed at the top compared to the speed at the bottom is equal to 1 over root 5. Now in scholarship there's been a couple of variations on this. Once you know basically this, you can then go, okay, well in this situation how high does it have to be? That sort of thing. So we could work out that. There's just getting to grips with vertical circles is what we're talking about here. So if v at the top is equal to square root of rg, we need to sort of have a think about how we're going to work it out. Now let's work with energies for a little while. Now the energy at the bottom is going to be equal to half mass times velocity at the bottom squared, right? Now the energy at the top is going to be equal to a half times the mass times the velocity at the bottom squared minus the velocity at the top squared, right? Now that's all got to be equal to m g 2r, just mass times height, mgh, mass times gravity times 2r. So we can actually cancel out those m's, can't we? And we've got g2r equals half of square root of b squared minus half of vt squared, right? So we can actually, once we do that, we can bring the 2 over and we can go, okay, so we've got 4gr is going to be equal to vb squared minus vt squared, right? So we're following all this? We've just said this, the energy at the bottom is going to be equal to that. The energy at the top is going to be equal to that, right? So the energy at the top is just going to be equal to the kinetic energy at the bottom minus that, and that's going to equal to the gravitational. So basically you've lost some kinetic energy, and that's equal to the gain in potential energy. Alright? And what we've basically said is that that means that 4gr equals vb squared minus vt squared. So vb squared is equal to 4gr plus vt squared. Just rearranging that, which means 4gr now what am I doing? 4gr vt squared, remember vt equals square root of rg, so vt squared equals rg is equal to vb squared, or 5gr is equal to vb squared. Alright? So vb must be equal to the square root of 5gr. You can see we're getting closer. So vt over vb is equal to the square root of gr over the square root of 5gr, which is equal to 1 over the square root of 5. So what were the tricky bits to do in here? Well, you already knew vt equals the square root of rg, and you could have worked it out. We started by looking at the energies, because the energies give us the v's. At the bottom we've got this energy of kinetic energy. Alright. Now at the top we've lost some kinetic energy but gained some potential energy, and the loss in kinetic energy, VB squared minus VT squared, right? So the loss of kinetic energy must be to the gain in potential energy. So I think that probably was the key, and going down that direction. Once you got that, we could get the 4GR was equal to this. We could then substitute in our VT, and we were pretty much there.